Hello,
Hello.
can you hear me?
Yes, sir.
What's happening? What is going on in your Fiji classes?
Fiji, they're doing area under curve.
Hmm.
I'm
And,
doing
and in physics?
probability. Acha. In physics, they will start induction and AC.
Hmm. And
Bas.
Satyaki is doing modern physics or wave optics.
So he has almost finished wave optics. So now he
Okay.
may start with the
Hmm.
yeah, he's doing wave optics का एक और class बाकी होगा.
Okay. Okay. Uh, so we'll continue from last class where we were discussing adjoint and inverse and how to get inverse of a matrix, right? So I'll just quickly revise what is an adjoint, how to get an adjoint. So what do you remember? Any matrix, suppose 1 0 2 3 4 1 0 0 1. Any square matrix. So this is some square matrix called A. How to get adjoint? First step is take cofactors of each element, right? Take each element's cofactors. So from here, cofactor here will be 4 into 1 minus 0. So 4. Cofactor here will be 3 into 1 minus 0. So 3 and minus 3, right?
Yeah.
And cofactor here will be 0 minus 0. So 0. Similarly, cofactor here will be 0 minus 0, 0. Cofactor of this element will be 1 minus 0. So 1 only. And cofactor,
Sir,
huh?
so to find a thing, you have to just take out the row and the column, no?
Correct. Yeah. Yeah. So
And then
0
enter the
minus
matrix.
minus 8, but keep in mind the sign also. So sign, this is negative. So 1 minus 6 minus 5 negative is plus 5. And finally, uh, 4, 4. That's it. This is the cofactors. This is the cofactor matrix. And after that, you have to take transpose of that. Transpose of that is the adjoint. So transpose of this matrix will be 4 minus 3 0 0 1 0 minus 8 5 4. Transpose means aij becomes aji, right? Correct.
Yes, sir.
So we get transpose of a matrix. This is the adjoint. Adjoint of A is equal to this. And inverse has a third step. To find inverse, there is a third step. The third step is basically do 1 by det of A of adjoint of A, right? So det of A, how will you find here? Det of A by Saras's method, 4 plus 0 plus 0 minus 0 minus 1 minus 0 and minus 0. 4.
Zero only. Yeah.
4 is the det. Okay. So this becomes 1 by 4 of this matrix. 1 by 4 of 4, 0, minus 8, minus 3, 1, 5, 0, 0, 4. That matrix turns out to be 1, 0, minus 2, minus 3 by 4, 1 by 4, 5 by 4, and 0, 0, 1. This matrix is your inverse matrix. Now, how will you quickly confirm that this is the inverse? You should see that multiplication of this with this should give the identity matrix, no?
Yeah.
Correct? So identity matrix will be 1, 1, 1 here and everywhere else 0, right? So when you multiply, quickly you can check multiplication by checking this position. So this into this vector, right? Dot product. So 1, 0, and 0. 1 is coming here. Let's check this position. So this position will be this and this dot product. 4 into 1 by 4 is 1, right? Everything else is 0. And last this position is this and this vector, right? So
Yeah,
you do
correct.
1 comes again, right? So it is coming identity. You can check any other element will be 0. If I want to check this particular position, I should check first row and second column, right? First row and second column. Now if you see, it is becoming 0, right? Every other element is 0. So this is basically how to find adjoint and inverse. Now what we will do is some properties of adjoints and inverse. Okay, so the first property that we'll look at is what is A into adjoint of A. A into adjoint of A is the same as adjoint of A into A is the same as det of A into I. Right. So how will we understand this property? First of all, what it says is A and adjoint A are commutative with respect to multiplication, right? So we have defined inverse as what? Inverse is equal to 1 by det of A adjoint of A, right? This is our definition of inverse, right? So I can be written as what? A into A inverse, no? Or it can be written as det of A into A inverse into A, right? Correct?
Yeah,
And since inverse is defined as A into 1 by det of A adjoint of A is same as A into 1 by det of A adjoint of A, right? You are getting the result, right? You are getting A into adjoint A is the same as adjoint A into A, right? Correct. Are you understanding what I'm saying?
yes,
So this is A and adjoint A are commutative with respect to each other, and the value is just what is this matrix going to look like? This matrix is going to look like this: det of A 0 0 0 det of A 0 0 0 det of A, right? This is the product of A and adjoint A. This is the answer of the product of A and adjoint A. Okay, because det of A is a scalar, is a number, right? You multiply that by a matrix, this is what happens. Now the second property that we'll look at, which you can prove for yourself, is adjoint AB is the same as adjoint of B into adjoint of A. Adjoint of AB, the matrix, first do the multiplication of AB and take an adjoint of that matrix, will be the same as adjoint of B into adjoint of A. Okay. Now, this looks similar to the formula that you had AB transpose, right? Is equal to B transpose A transpose, right? Just like that, this is also true. When you do the transpose operation, the AB reverses itself, no? Similarly, when you do the adjoint operation also, the AB reverses itself. Obviously, the reason of the reversal is because this is not just a simple cofactor matrix. No, this is a transpose of the cofactor matrix, right? Remember in the definition,
yes,
when you take adjoint of AB, you don't just take cofactors of AB, you also take a transpose, right? That's why, because transpose follows this property, that's why this is also reversing. Is everyone understanding? Correct? You can confirm it with some calculating some adjoints and all for some reason, but that will be long, so I'll not do it right now. Okay, so we move on. The third property is adjoint of k times a. K is a number, is a scalar. K is a scalar. Adjoint of ka is equal to what? So Molly, do you know this?
But I don't like. I do not remember these things.
Why you have done? No, this matrices
Like,
determinants. It's over, no, Alan.
yeah, but I don't remember it. Like, just keep it in my mind.
K power n minus 1 into adjoint of A, where n is the order of matrix A. Order means it's a square matrix. No, it's 3 cross 3, then n is equal to 3. If it's a 3 cross 3 matrix, adjoint of K times A will be K square into adjoint of A. Now this we'll have to check. So let's just do it for a 2 cross 2 matrix. So A, B, C, D, right? 2 cross 2 matrix. Let's find the adjoint. Adjoint will be cofactors. Cofactors will be, first cofactor is D, B ka cofactor is C but minus C, and C's cofactor is B but minus B, and D's cofactor is A. This is the cofactor matrix. I do a transpose of that. So transpose becomes D minus C minus B A. This is my adjoint, right? Adjoint of A, right? So what is the value of adjoint of A into K square? A into K square, but K square was for K power n minus 1. So K power, here order of this matrix is 2, no? It's a square matrix of order 2. So it should be K power 1. So adjoint of K power 1 will be KD minus KB and minus KC and KA. On the other hand, if you try to do the left hand side, so instead of this, suppose you had KA, KB, KC, KD. So everything will just be, this will be KD, KC, KB, KA, right? So that is, and then you take transpose, it becomes K, 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 K. So isn't it the same? K times D minus B, C minus C, and A, right? That is the same as this, correct? If you had taken a 3 cross 3 matrix, so let's do that example. Let's take numbers 1, 0, 1, 1, 1, 0, 0, 1, 1. Let's take a 3 cross 3 matrix. This is our A matrix, okay? I want to find out what is adjoint of 2 times A, okay? So the prediction is that adjoint of A should be 2 power n minus 1. N is 3. So 2 square adjoint of A. This is the property, okay? So this is what we'll verify right now. So first we'll find adjoint of A, then we'll find adjoint of 2A. So adjoint of A, tell me. Please calculate and tell me adjoint of A.
So,
Hmm.
so can you just show the thing again? Another property.
What?
Adjoint Ka in bracket equals to K power n pi minus 1 into Ka in bracket.
What? Adjoint of KA is equal to K power n minus 1 into adjoint of A. Why are you focused on copying the question, the things? Just listen, no, carefully. What is happening?
और
Why are
वहाँ
you
बीजू वालों
behind on
टाइम
the
पास
previous
करीब नहीं
screen? This is the property.
So I wasn't able to hear.
Huh?
So I wasn't able to hear when you're teaching this.
Why are you not able to hear, dude? What is happening to your
So there's
connection?
construction material happening big time.
Can you hear right now?
So now I came out of the room. Yes, sir.
This is the property. This is the property we are trying to verify. How do we verify it? First, find adjoint of A. Finding adjoint of A means
cofactor का
finding
transpose
cofactor and root transpose. So let's do cofactors quickly. 1 minus 0,
1
1. Then this cofactor is
minus 1
1 and put a minus sign. This cofactor
1
becomes 1. This cofactor should have a minus
minus
sign.
1 so plus 1 1
So plus 1. And this one
1
1, and this one
1
1 minus 1, right?
yeah fine
and this one becomes
-1.
-1, 0,
One.
-1,
1.
+1, right? And
Yeah.
this one becomes 1.
Yeah. It is
Okay.
same, yeah.
So this is the thing. Now you do a transpose. Transpose becomes 1, -1, 1, 1, 1, -1, -1, 1, 1. This is my transpose. This is my adjoint of A. Now adjoint of A, if you multiply by k to the power n minus 1, so 2 square, so 4. This should be the value of adjoint of 2A. So adjoint of 2A would be, I don't want to do it, but you guys can do it.
So n means agar it's a 3 by 3 matrix, then n is 2.
Hmm?
So what is n in that thing?
N is order of the matrix. N is 3.
Okay.
3 by 3 है तो n is 3. N minus 1 is 2. So this matrix, if you want to do, what you will realize very soon is 4 will keep coming in every term. No, see, cofactor matrix will keep getting 4s. No, if you do cofactor matrix of this, first few terms only let's do. Cofactor of this is 4, and then this is 4 minus 4, correct? And
4.
this is 4. So everywhere 4 is coming, no, in the cofactors. When you do transpose, it will become 4 minus 4, 4, like this, right? So see, that is the same here. No? At least one column you can see easily, right? Sparsh, are you understanding what is happening?
Yes, sir.
So we have verified that this is happening. So the property is simply this, that adjoint of some scalar multiplied by some matrix is equal to scalar power n minus 1 into that adjoint of that matrix, where n is the order of that matrix, right? Okay. So then we come to adjoint of fourth property. Adjoint of a power m is the same as adjoint of a whole power m. Again, we'll not prove it. It is going to be slightly annoying to prove, but you can confirm it for some matrix. So a square you can try and see, right? Adjoint of a square you can find, and you have to prove that it is adjoint of a whole square. Take some simple matrix and check this condition, right? So the power can go outside like a simple exponent. So that is a nice property. Fifth property is adjoint of a diagonal matrix. Adjoint of a diagonal matrix. What is a diagonal matrix? Is also a diagonal matrix. What is a diagonal matrix? A diagonal matrix is one which has elements only, non-zero values only on the diagonals. Everything else is zero. So if there is a matrix like this, A, B, C, adjoint of this matrix will also turn out to be a diagonal matrix. That is the property. Okay. So this you can easily verify because so many cofactors will be simply zero. No. The only cofactors which will not be zero will be on the diagonals here. You can see it easily. So this cofactor is BC. This cofactor is 0, no? You remove these rows, so you get, 1 second. What is this cofactor? AC, right?
The side will be 0.
AC होगा ना? Minus AC.
Yeah, minus AC, correct.
0, B0, 0, 0, C. So what is coming?
First one is BC.
Second one is?
Minus AC.
No, it is 0 only. What am I saying? Remove this.
Okay. Yeah.
I'm making a mistake, then everyone is agreeing. Then after that, I'm correcting it, then everyone is agreeing with that also. What is happening, guys?
What?
You guys should also notice things. No, I'm saying minus AC, then nobody is saying wrong.
I didn't see. I'm just assuming you're doing it correctly.
Great, great.
This also 0.
Everything
Blind
will be
trust.
0, 0, and here this one when you do, it will be AC.
Minus AC.
Minus AC nahi AC. This is the cofactor matrix. When you do transpose, it is still going to be the same itself, right? Transpose is the same. Diagonal matrix transpose will be the same. This is your adjoint. So notice that the adjoint is itself also a diagonal matrix, right? So that is the property. Then we come to some more properties, 3 more properties. Sixth one is saying adjoint of A is equal to, okay. So now here, what does it mean? N is the order of the square matrix. N is the order of the square matrix A. N is the order of the square matrix A. Adjoint of A is equal to det of A to the power n minus 2 into A. So this looks annoying to check, but we will check anyway because this is very useful property. These are the types of complications that are given in any JEE exam. Like it will not be some easy thing. So you're doing adjoint of A. So let's just do it for some matrix. So let's take a 1, 3, 0, 2. Let's take a 2 cross 2 matrix only for now. So adjoint of A we want to find out. Adjoint of A is 2, 2, and this one will be 0. This one will be minus 3. This one will be 1, right? And transpose, right? So it becomes 2, 0, minus 3, 1. Correct? This is my adjoint of A, right? Correct, no?
Yeah.
So I want to do adjoint of this also. So let's do adjoint of this. So this becomes 1. This becomes 0. This becomes minus 3, but 3. And this becomes 2. This is cofactor. Transpose becomes 1, 0, 3, 2, right? Correct. 1, 0, 3, 2 is the transpose, no? Correct, no?
That I'm seeing.
Uh,
2 minus 3 transpose.
we have done adjoint of A, right?
Yeah.
We got adjoint of A here. We did cofactors here. We did transpose, and this is adjoint of A. Correct?
Yeah.
So now what we got here is the same matrix is equal to A. It is coming, no? Right? So that verifies the property, at least for square matrices, that adjoint of A is equal to det of A whole to the power 2 minus 2 into A, right? For square matrices, correct? Which is equal to det of A to the power 0. So it's same as A, right? Square matrices of order 2, adjoint of A is the same thing. Correct? Det of A here was what? Det of A here was 2. Makes sense?
Yeah.
So this property has been verified right now for square matrices of order 2. You can, we should do it for, say, order 3 matrix, some easy matrix for order 3. 1, 0, 3, 0, 2, 0, 1, 0.
So these rules are only for square matrices.
Only for square matrices, inverse, adjoint, and all are there.
Oh.
So this is my order 3A matrix. Now let's find our adjoint of A. Adjoint of A. So let's do it. 2, and this one is 0 minus 0, and this one is 0 minus 2, so minus 2 only. This one is 0 minus 0, and this one is 1 minus 3, minus 2, and this one is 0 minus 0, 0, and then this is 0 minus 6. 1 plus 3, 4, and 0 minus 6, minus 6. This one will be 1 minus 0, or 0 minus 0, and this one will be 2. This is my adjoint of A. Transpose of this is my adjoint. So my actual adjoint of A is 2, 0, minus 2, and 0, minus 2, 0, minus 6, 0, 2. This is my adjoint of A. Everyone is agreeing with that, no?
Yeah.
Okay. Sparsh, you are getting it, no? Sparsh?
Yes, sir.
So find out adjoint of this matrix, adjoint of A, right? So let's see. Iska cofactors will be what? Minus 4, 0, and this one will be minus 4, and this one will be 0, and this one will be 4, minus 4, minus 12, minus 8, and this will be 0, and this will be 0 minus 12, so minus 12, and this one will be 0, and last one is minus 4. That's it. And take a transpose, so that becomes minus 4, 0, minus 4, 0, minus 8, 0, minus 12, 0, minus 4. Correct? Now what is det of A? Det of A by Saras's rule: 2 plus 0 plus 0 minus 6 minus 0 minus 0. Det of A is minus 4, no? Correct?
Yeah.
Correct? And now the property is easily verified. Minus 4, det of A to the power n minus 2, right? N minus 2 is 3 minus 2 multiplied by A, basically is minus 4A, right? Minus 4A is equal to definitely this, no? Adjoint of A, right? See?
Yeah.
स्पर्श हो रहा है ना? Adjoint of A had come as this. Correct?
Yes, sir.
So the property we have confirmed for multiple types of matrices. Adjoint of A is equal to det of A to the power n minus 2 into A, right? So for 2 cross 2 matrices, adjoint of A is same as A. And for 3 cross 3 matrices, which is what you are likely to see most of the time, adjoint of A for 3 cross 3 matrices will just be det of A into A, right? These are the two special cases that you are most likely to see. Correct? Okay. So now next property. This everyone has understood. This is very important.
Yes, sir.
Seventh one is det of adjoint of A is equal to adjoint det of A to the power n minus 1. So this is easy to prove because we have the earlier property. We had one, no? We had A into adjoint of A was equal to adjoint of A into A was equal to det of A into IN, right? This was the first property that we had written, right? Correct.
Yeah.
So
Yeah.
just take det of two sides. Let's take det on both sides. Det of A adjoint A is equal to det of A into IN, right? This is a scalar, so this comes out. Det of A into det of IN is 1. So this becomes just det of A, right? And here you get det of A into det of adjoint of A. Oh wait, I have made a mistake. Det of IN is not this. This is A power n, by the way. Think about it. Det of the scalar comes out, but it is A power n, no? Think about it. Det of A into this matrix was what? This matrix was like this, no?
Yes, sir.
If it was a 3 cross 3 matrix, 3 cross
Means
3
more
identity.
be more in
Huh?
power, this thing power n, yeah.
3 cross 3 identity matrix, then det of that is this power 3, right? So if it was 2 cross 2, it would have been this power 2. So this side det, when you take det of this side, it becomes det of A to the power n, right? And this becomes det of A into det of adjoint of A is equal to det of A to the power n. Therefore, det of adjoint of A comes out to be det of A to the power n minus 1, right? So basically what we are saying is that this property follows from the first property. You take det on both sides and be careful that det of mod A in is not det of A, it is det of A to the power n, right? Where n is the order of that matrix, right? This is clear, no? I hope this is clear for everyone.
Yeah.
Sparsh, done this one? Eighth one is det of adjoint of A is equal to det of A to the power n minus 1 whole square. N minus 1 whole square. Now earlier we saw one property which was adjoint of A was equal to det of A to the power n minus 2 into A, right? This was property number 6 that we had seen, right? So we are taking det of this. So det of adjoint of A will be equal to
Yeah,
det
mod
of
A, this thing.
A n
Power
minus
n.
2 into A det, right?
Yeah.
So now this will become what? So this is just a number, right?
A determinant of some number times the matrix is that number power the thing number n.
Determinant of some k times A, right?
Is k power n a, determinant a, right?
It should be k power na, I think. K power na if it's a square matrix, right?
Yeah.
So should it be that?
I mean, came in the last question, last property, the thing, right?
No, that was
Same thing, right? Determinant.
we had done it. We had done I, right?
Yeah. So the mod I is.
It had come out as k power n mod I, right?
Is that one?
Yeah. So here, if you do this, it should become det of A to the power n minus 2 to the power n or something, no?
Yeah.
Into det of A, right?
Yeah.
So, correct. See? So this becomes det of A to the power n square minus 2n and det of A, right? So that is det of A right?
Yeah.
So we are using again this property. Det of some k times A is basically k power n into det of A. So you have n minus 2 into n and det of A. So det of A to the power n square minus 2n plus 1, right? So we have figured out what to do about these. This matrix is equal to this matrix, and det of this matrix is equal to det of A to the power n minus 1 whole square. Okay, so these are going to come in handy. I hope everyone has understood everything here. Now we come to inverse and all. So now we come to properties of inverse. Inverse is defined as inverse of A is a matrix B such that B into A is equal to A into B is equal to I. Inverse is defined only for square matrices. Only for square matrices it is defined. Internet got disconnected. Sparsh is not there.
Yeah. He's not there.
Oh, since when? Just now. Wait. Let him come back. Otherwise, he will say that I have gone ahead. So, how are things at home for you? What is happening these days?
Studying.
Studying, huh? Properly you are studying or like chilling also?
Sir, more properly now
More properly now than before also.
than before also.
Okay. Oh, how was your test? Like there was some test yesterday.
Yeah.
How was it?
It was good. Like I don't know, the result will come and get to know exactly, you know. It was kind of hard, like with of course, like if you
Mains
compare to the
pattern
other
only.
tests. No, it was advanced.
Advanced pattern.
Yeah.
You got the paper.
No, it was online, so we don't get to see the paper after that.
You don't get the PDF, nothing you get.
No.
Oh, okay. And the syllabus was what?
In maths, it was the differentiability and all.
Till where?
No, just differentiability. Because before all that was there, like finished over before. In chemistry, entire organic was there.
Entire organic, is it?
Yeah, pura
Till
like
where?
till carboxylic acid and all.
Till there you have finished chemistry, no?
Yeah.
And is your chemistry class going with the teacher that you had? One more teacher, some teacher.
Yeah.
How is it going?
Okay.
You are getting it, no?
Yeah.
I mean, make sure that you are getting as much benefit as possible and understanding everything.
Yeah.
Are you reading from some standard book? Is he telling you to read from at least some good book? How are you doing chemistry organic preparation?
Right now I'm doing so first like I didn't do it properly when we were doing it in tuition because I don't know, I wasn't very comfortable with how he was doing it or whatever. So I did it on my own. So I finished the theory and all from my Allen books. I referred a few books and I collected all the theory I could. And now I'm doing questions from these books, which are apparently some very, very good books.
Like which one?
One I'm doing is
MSc.
Yeah.
Balaji Publications, MSc.
Yeah. And I'm doing one more book. I forgot the name of that. But
one more book which is Indian writers only.
I do that book, I do Allen book, and I do Yeah, I think it's Indian only.
Okay.
I do another book which is this Pearson organic chemistry.
That is Pearson, but it's
Peter
like
Sky
for
or something. Yeah.
it is Indian guy, or is it
No, no,
Peter
no.
Sykes?
Yeah.
Peter Sykes, are you reading? It's a
Yeah.
tiny book.
Yeah. But so my old teacher, he had told me that this book is very good. So
Peter Sykes, you should read. You can practice questions from wherever you're doing, that's fine. But ultimately, you have to understand all the mechanisms very well. Like every mechanism, you need to know exactly how it is happening. Right? That is the main thing in this.
yeah, there's a lot of stuff going on.
Yeah, there is a lot of stuff going on, but there is no chance that anybody can remember it all. Okay, you have to like understand it and know how reactions happen rather than trying to remember all reactions, right?
Yeah.
It will not work if you try to remember products and all here.
Yeah.
It's too much stuff. Okay, so I hope the mechanisms of all of the functional groups, how each functional group behaves, all of that is clear.
Pretty
Get
much.
that sorted out and read Peter Sykes. Peter Sykes is good. Yeah. And how was so organic test? How did it go?
The test was okay, I guess. I don't know.
Answer keys and all are not out.
They'll come like after 2 days. So it was yesterday, it'll come maybe tomorrow or something. The result will only come tomorrow.
Result will come tomorrow.
Yeah.
Okay. Okay, wait, I'll message first to come back. Like I have just said, okay.
But he thought, it's fine, don't come back.
I hope he's desperately trying to come back right now. And maths paper was how advanced were you able to do?
Maths was okay. I did like, I did quite a few questions.
Differentiability and all, so they would just give different functions and count number of points and all of that stuff,
Yeah,
right?
how many points are not differentiable and all that shit.
Yeah. You just have to keep following definitions and all the time.
Yeah, but it's long, some questions are pretty long.
And physics, what was that portion?
Physics, we have electrostatics, gravitation, and electricity.
That is some old stuff only. Like I hope it was good.
Yeah, physics was good.
Okay. One or two classes, this will be over. Like then we'll start revision. We'll start doing tests. He's unable to join. Okay. Okay, fine. So we'll continue here. So Sparsh cannot join right now. Okay. So inverse of a matrix is defined as this, and it's a matrix B such that this happens, and we know how to find B. B is equal to 1 by det of A adjoint of A. This is the thing. Okay. So now we'll come to some properties, some basic properties of matrices, like AB inverse is equal to B inverse A inverse, right? This is the first property. I will not do any derivations for here. This is going to just be long verification. You
You
can
have to
check.
like put determinants and check
Yeah,
it.
you have to try to get determinant. Try to get inverse of this by the definition. Inverse of this would be 1 by det of AB and adjoint of AB, right?
Maybe.
And
Yeah.
adjoint of AB is adjoint of B into adjoint of A, right?
Yeah.
Now, okay, it's not so long, right? And then take this grouping. This is just, and this grouping is A inverse, right?
Yeah.
So that is the proof. Then second one is A transpose inverse is the same
A
as
inverse transpose.
A inverse transpose. Okay. Then the third rule is what is the det of adjoint A? Did we do that already? Yeah.
We did it.
Det of adjoint A is this to the power n. Oh, we did it
Yeah, A
already.
power. Yeah.
Yeah, yeah. Okay. So, okay. Fourth one is det of A inverse is equal to det of A to the power inverse.
Wait, how can you take inverse of a number? Ah, oh, okay, like that. Like
Uh,
1 by. Okay.
Basically, because this comes because simply this is 1 by det of A adjoint of A, right? And
Yeah.
you're taking det of that, right? So that should be equal to
Adjoint of A का det
uh,
is A power
1 by A power n, right?
by
Into
ऊपर n minus 1 हो जाए.
adjoint of A, right?
Yeah.
And on top there is n minus 1.
Yeah, yeah. Please come in.
So this becomes 1 by det of A. Normally you should not be able to do that, right? Your doubt is genuine, but this comes in this case, right?
Yeah.
So, okay, so this is one thing. Then for a matrix, so for a 2 cross 2 square matrix, you should just remember what is adjoint of A.
Yeah,
And
that
what
is
is adjoint of A in this case is D A minus B
C
minus C, and inverse of A is equal to
is that
obviously
by
1 by AD minus BC into D minus B minus C A. So you reverse the diagonal and put minus signs on the others, right? Okay.
yeah.
Then we have a property that says A to the power K inverse is going to be equal to A inverse to the power K. Okay. This is true. So you can just think about it in the same way that you were
We
thinking
did the
about.
above, yeah.
Yeah, we did AB, no, that way.
Yeah.
AB inverse was B inverse A inverse. Similarly, you can show this also if it is K, some number. So this is fine. Then for a okay, so one property says that if the inverse of a symmetric matrix if it exists is also a symmetric matrix
Are these statements also important?
Yes, these statements are important because sometimes these statements will simplify your work. You don't need to do, like, you can just verify whether it's symmetric or not. No, so for example, like, you don't need to find exactly everything, right? If you know this fact. So for example, let's take a symmetric matrix. Okay, this is my standard coordinate geometry symmetric matrix, right?
Yeah.
Now
We're gonna take the inverse of this?
I will just take some cofactors, right? I will take some cofactors. A11 is what? A11 is BC minus F square,
Yeah.
right? And A22 is equal to AC minus G square, right? AC minus G square. A33 I
AB
don't
minus
need
H
to
square.
find. A33 I will not find also. A12 is what? A12 will be
HC minus GF.
HC minus GF, but minus sign,
Yeah.
right? So that is GH is equal to
GF minus HC.
GF minus HC. And now what was A21? A21 is what?
Second. HC minus HG.
HC 21.
Minus FG.
HC minus FG, but minus sign, no?
Yeah.
So that is the same, no?
Yeah.
So this A21 is becoming same as A12, right?
Yeah.
So that means when you take the
Transpose also will be the same.
transpose also, it will be the same. So
Symmetric only.
it should be symmetric. You can verify other elements like this, right?
Yeah.
So it will be symmetric. So inverse of a symmetric matrix will come also symmetric. So that is the property. Then, okay, let's do a question. Let's do a question. Like most of the properties are done. So yeah, let's do a question. If A is equal to 1 0 minus 1 2 1 0 3 1 1, find det of adjoint of A. So we know this, right? We know a property for this,
Formula only.
right?
Yeah.
I think this was a formula, no?
Yeah.
You can refer back to the old property. What came earlier?
This is only right.
Yeah, this is what came.
Correct.
So that is very easy, because now det of A you can easily do by Saras's rule. Det of A you need to find, no? So
yeah.
So 1 plus 0 plus
minus 2
minus 2 minus this one. So minus 3 minus 0 and 0. So this becomes 1 minus 2 plus 3. So 4 minus 2 to 2, right?
Sorry, 2, yeah.
So 2 is coming, 2 to the power 3 cross 4. That is the answer.
I'll just write this down.
What?
This last one, I'll just write that down.
What are you saying? I can't hear you.
I'll just write this property down 1 minute.
Yeah. Which property?
This one. I didn't write this one. I forgot about it.
This one?
Yep.
Yeah. Next question is, for the matrix for A is equal to 3 1 7 5, find x and y such that A square plus xi is equal to ya. Hence find A inverse. Hence find A inverse means you have to use this to find A inverse, which is nice because you can multiply everywhere by A inverse. So this becomes A inverse A square is A plus x A inverse is equal to y I, right? So basically A inverse is equal to yi minus A by x, right?
Yeah, A inverse is
basically this. So you have to find, if you can find x and y here, you will get A inverse without doing the normal method, right? Correct. So A square will be simple, 3175 into 3175. That is simply dot product 339 plus 7, 16, dot product 31 plus 5, 8, and 7 3 21 plus 35, 56, 7 plus 25, 32, right?
Yeah.
Right. So this is a square plus xi, right? So
X.
after doing xi, it will become 16 plus x,
Yeah.
8, 56,
32
32
X.
plus x should be equal to y times a, right?
Yeah.
So that is 3y is equal to 16 plus x, and y times a, y is equal to 8, right?
32.
So 24. So x is equal to 8 also,
Yeah, how do you get y is equal to 8?
right?
Oh, 15. Oh, okay.
This one, second term. yi, right?
Yeah.
Y is equal to 8. X is equal to 8, y is equal to 8. So this is just 8i minus a by 8, right?
Yeah.
So that is just I minus 1 by 8a, right?
Yeah.
So 1 by 8a is 3 by 8, 1 by 8, 7 by 8, 5 by 8. And you have to do I minus. So this becomes 5 by 8 minus 1 by 8, minus 7 by 8, 3 by 8, right? This is your inverse,
Yeah.
right? So that is the answer. We have done it without doing the 5 minus 1, 7, 3. Yeah, correct.
Yeah.
Okay. We have done it without doing adjoint. We could have done it in a different way also. We could have said that inverse is easy to find because it's a square matrix, right?
Yeah.
We could have just gotten inverse
You
first.
can just write I is equal to A into something and then find that something for this case. Like just write xi is equal to ya minus a square.
Yeah.
So then take a common. So you get yi minus a. So I is equal to a into yi minus a by x. So that is the inverse. That's how I do
What
it.
we can, instead of doing it like this, we could also do it by saying that inverse of this is very fast to find. No?
Yeah.
1 by
Yeah.
15 minus 7, 8 into, we
5,
replace
3
this
and
5, 3 minus 1 minus 7, right?
yeah.
That is the inverse. You already know inverse. So we know this matrix, we know this matrix, and we
You
know
just
A
find.
matrix. So you just find x and y, right?
Yeah.
Correct. That is also a way to do it. Then we go ahead. Okay, so we go to some special types of matrices. Special matrices. So first is orthogonal. Orthogonal matrix. So what is the meaning of an orthogonal matrix? Is if a square matrix A, okay, is orthogonal, then that means, do you remember anything?
Yeah, that A transpose into A is some I or something.
Correct. A into A transpose is I. So now what does it really mean, this property? So think of it like this: A, B, C, D, E, F, G, H, I, and A transpose would be what? A, B, C, D, E, F, G, H, I, right? Is equal to I, right? So 1, 0, 0. Okay. This is the meaning of this matrix being orthogonal, right?
Yeah.
Now think of what it really means. See, when you do the multiplication, you have to do dot products of these two vectors, no?
Yeah.
So orthogonal matrix, the property implies that A into A dot product becomes what? See, A square plus B square plus C square is equal to 1. Now see, this into this, so D square plus E square plus F square is equal to 1, and G square plus H square plus I square is equal to 1. And also when you do any other dot product, right,
Yeah.
it should be 0, right?
Yeah.
AD plus BE plus CF is equal to 0, and AG plus BH
plus
plus
CI.
CI is equal to 0. Similarly, you'll get this dot product is also 0, which is the same thing. This is the same thing, CF. And third one is G into D, right? GD plus HE plus FI, right, is also 0, right? Correct.
Yeah.
Now these 6 equations have a very nice meaning. Like why would you give the name orthogonal, right? The meaning is that these a matrix is orthogonal, a 3 cross 3 square matrix is orthogonal if all the 3 vectors, if you think of it as 3 row vectors, right?
The modulus is 1.
Their modulus is 1 and they are perpendicular to the other 2 rows.
Yeah.
See, perpendicular
The dot
AD
product is 0.
dot product is 0. That is the condition, right?
Yeah.
AG, right? And G and D, right? Correct.
Yeah.
Row vectors also and column vectors also, you can think of it. All 3 column vectors also, A square plus D square plus G square should also be 1. No? I think it will come if you.
No, I don't think about it. You can't tell like
The idea that one row vector only you can do is going to be, I don't think it's just for row vectors. I mean, the feeling is that what is valid for row vectors should also be valid for column vectors, but okay, right now it doesn't seem to be coming, right? A square plus D square plus G square, B square plus E square plus H square. AC plus DF plus GI, AC plus DF plus GI. Okay, so right now it is not
wait,
obvious.
1 minute. If you take like it can also be A transpose into A and A
Yeah,
into
yeah.
A transpose both,
Yeah,
right?
yeah.
So if you switch them, then will you get the opposite addition?
If you switch them, A transpose into A should be, oh wait, A and A transpose, if they are symmetric, right? Are they symmetric?
No.
A transpose into A.
Will some different equations come or the same equations will come?
Equations will be
different. Then you'll get A square plus D square plus G square.
So instead of this writing here, I will write this here, right? So you'll get A, B, C, D, E, F, G, H, I. So in this case, you'll get this into this, right? A square plus D square plus G square, right?
That is also then this thing.
Right. In this case, you are getting column vectors, right? If you wrote it like this.
Which is also equal, yeah.
So I'm thinking that A transpose A and A transpose are same.
Yeah.
Is it same? For any
in
vector
this
A.
Case.
For a square matrix, is this property true? In this case, nahi, I want it to be true in any case, right? Then
yeah, if you just take A transpose is equal to I, then if you take transpose of it, then it's like A B transpose is B
correct.
transpose A transpose, right?
Correct. Yeah. So it is working out, right? So because in this case, when you take transpose of it, you get A into A transpose, right?
Yeah.
I mean
A transpose into A. You get both.
But that becomes A in transpose only. Oh, that's fine. So okay, fine. I think it is valid for both column vectors and row vectors, but I will just confirm it once. Okay.
Because A B transpose is B transpose into A transpose. That's how it's coming.
What I want you to know is that the row vectors are modulus 1 and they are perpendicular to each other. Each row vector is perpendicular to the other, right? So it is very easy for you to check whether something is orthogonal matrix or not. You don't have to actually do the multiplication, okay? You don't have to actually do this. Check whether each of them, each vector, right,
Yeah.
is modulus 1,
Yeah.
and check whether they are perpendicular to each other, right?
Just for row we can check, that'll be enough.
Just for row vectors you can check it, right? So
Yeah.
we will see examples of, for example, check whether this 1 by 3, 2 by 3, 2 by 3, minus 2 by root 5, 1 by root 5, and 0, and minus 2 by 3 root 5, and minus 4 by 3 root 5, and 5 by 3 root 5, right, is
Yeah.
orthogonal or not. The first thing to check is check whether this square plus this square plus this square is 1,
Yeah, it's
right?
coming.
And this is 4 plus
It's also coming.
1. This is also coming. This is also coming, I think, because 4 plus 16 plus 25, right?
Yeah.
So 4 plus 16 plus 25 by 9 into 5, 45, right? 20 plus 25, this is also coming, right?
Yeah.
Now dot product, dot product, dot product. Minus 2 by 3 root 5 plus 2 by 3 root 5, 0.
Yeah.
Dot product, dot product, dot product, right?
It's coming
4 by
0.
4 minus 4. So this is orthogonal. So you didn't have to actually do the property, right? If you don't know that, then you will have to like actually do it and check. That will be super annoying.
Mm.
Okay. So orthogonal matrix. So some properties are, if A is orthogonal, A transpose is also orthogonal. That's why the other property also comes, right?
Yeah.
What we were just saying, column vectors also you can do the same thing. Okay. Then for any two orthogonal matrix A and B, AB and BA are also orthogonal.
Yeah.
We can confirm it. If and third property is A is orthogonal, then A inverse is also orthogonal. So just make a note of these properties. These are going to be useful. Orthogonal definition and meaning, and then properties. 3 properties. Okay. How do you check orthogonal matrices? You check by this method. Okay.
Yeah.
Okay, we'll go ahead. Orthogonal matrices are done. Second type of special matrix is idempotent matrix. This is a matrix if A square is equal to A. It's called idempotent.
Yeah.
Right? So now there are some nice properties for this as well. If A and B are two idempotent matrices, then we have AB is also idempotent.
Yeah.
If and only if AB is equal to BA. So for example, what does it mean? We have AB will be
So that's
idempotent.
because of that thing, right? If you square it, then that
Correct.
instead of 2AB, you get AB plus BA.
See, this is the real meaning of doing AB into AB, right?
Yeah.
But if you can replace this with AB, right?
Then come A square, B square.
Then it will come A square, B square, and that will be AB.
Yeah.
Right? So this has to happen. This step has to be true. A and B should be commutative with multiplication only. Then we will get this property: AB whole square is equal to AB. Right? So then AB will also be idempotent. Then second one is A plus B is idempotent
If AB is going to be B,
Yeah.
AB is going to be A.
if AB is equal to B. Again, same logic.
Yeah.
And third one is AB is equal to A and BA is equal to B, this
also
implies A square is equal to A and B
B square
square is
is
equal to B,
yeah,
right?
this is done. Yeah.
So why is this true? Because AB is equal to A means that B is equal to A inverse, right?
Like if you just multiply A, right, you get A square, B is equal to A square.
A square B is equal to A
No, wait,
square.
multiply on the right side. So we get A is equal to A square
Okay.
or something like that. Wait. And then you replace AB as A. No, wait, BA.
What are you
What the
saying?
heck am I saying? Ah, I got it. BA, you write it as B. You get
BA I write
AB.
as B, yes.
Yeah.
AB as A
So,
square.
so then AB is A, which is equal to A square.
Great.
See?
Yeah. But don't just say the final step without thinking about it.
Yeah.
Great. This time by fluke it came, but otherwise you would have been saying like random. Just replace AB with A. Yeah. Okay. So you can prove it by similar methods, right?
Yeah.
I will leave that to you. Then, okay. Then we have some properties of this diagonal matrices, right? Wait, let me think. A is an idempotent matrix. Okay, one property, let's see. A is idempotent and A plus B is equal to I. Then B is idempotent and AB is equal to BA is equal to 0 matrix. Why? Let's check whether this is true or not. A is idempotent means A square is equal to A.
So multiply by A.
And A plus B is equal to I, then you can do A plus B whole square is equal to I, right? So that becomes A square plus
B
B
square
square plus AB plus BA.
is equal to I.
I. And A square is equal to A, correct? So
Sir, in this A plus B is equal to I, no. If you multiply A, so you get A square plus BA or AB, whatever. You can do any. Is equal to A. Is equal to A.
Is equal to A.
So then A square and A get cancelled. So BA is equal to 0 we get. Same thing we get AB also is equal to 0.
You get these two zeros, then you can put 0, 0 here.
Yeah.
So this goes away. So you get A square plus B square is I. So A square plus B square is equal to I is equal to A plus B. And A square is equal to A. So B square is equal to B.
Yeah.
Which implies B is also idempotent. Okay, so there are many ways in which you can prove this, but clearly this was a crucial step to prove that AB and BA is equal to 0. And after that you multiply and check, right? So okay, this is one. Then 5 is a diagonal matrix. Diagonal matrix, say 1 1, all the diagonals are 1, right? So this is basically an identity matrix. That is obviously also idempotent, right?
Yeah.
If okay, okay, let's find out when is a 2 cross 2 matrix going to be idempotent, right? When is a 2 cross 2 matrix going to be idempotent? So what we want to find out is condition that 2 cross 2 matrix is idempotent. So let's let's take a random 2 cross 2 matrix A, B, C, D, A, B, C, D, right?
Okay. Yeah.
So what is the
A square
product?
plus B square. A square plus
A
BC.
square plus BC and AB plus
BD.
BD and AC
AC plus
plus
DC.
DC plus CD and BC plus
D
D
square.
square. BC plus D square. So this is equal to
A.
A, right? This should be equal to A, B, C, D. So let's look at the equations that come. A square plus BC is equal to A. AB plus BD is equal to
B.
B. AC plus CD is equal to C, and BC plus D square is equal to
D.
D, right? So
Yeah.
from these two, we can get B into A plus D is equal to B, and C into A plus D is equal to C, right?
Yeah.
So this implies B times A plus D minus 1 is equal to 0, right?
Yeah.
Right? And C times,
If it's
right?
not an identity matrix, then A plus D is equal to 1.
Yeah, wait. B, so there are two cases when this can happen. B can be 0 or A plus D is 1, right?
Yeah.
B can be 0. If B is 0, then C also must be 0, right?
Yeah.
This is weird.
Then becomes an identity matrix.
Then it becomes identity matrix. So that is a trivial condition. Let's not worry about it.
Yeah.
The other condition is A plus D is equal to 1, right? When these two equations are satisfied, right? If A plus D is equal to 1. So what happens to the other two?
We just add them.
We can just add them, right?
I think it will work.
So 2BC is equal to A plus D
So,
is 1. Okay, nothing nice is happening.
yeah, but we don't know what BC is.
So A plus D is equal to 1 means what? That D is equal to 1 minus A, right? D is equal to 1 minus A.
Maybe this is only the condition.
This is not a nice condition. The book is saying something, but I think it is wrong. So now I don't know. Book is saying something that trace should be 0. But trace is
You mean-
1, dude.
Yeah.
Trace of the matrix is coming for us 1, no?
1.
So that is not what I expected. Okay. Okay. There is nothing wrong with what we have done. So still, so there is no obvious condition that I2 cross 2 is idempotent. Right now, what we are getting is A plus D should be 1, right? Which is, otherwise it will be identity matrix. B and C are 0.
Yeah.
So yeah, okay. So that is a useless thing that we did. Let's move on. What is a involutory matrix? Not involuntary, involutory. So it is very related to idempotent. Involutory means A square is equal to I. Here A square was equal to A. Okay. This is just a definition thing. It's just a name that has been given. So there's no special property for this involutory. You don't have to worry about it. Nilpotent. These are all there in your Allen book, by the way. Nilpotent matrix is a matrix is said to be nilpotent if there is the positive integer m such that a power m is equal to 0. Okay, it is a nilpotent matrix of order m right now. If a power m is equal to 0 matrix. Okay,
Yeah.
and here m is the least number possible, least integer
For which it's
for
0.
which this is true, right? So
Yeah.
that is called the index of the nilpotent matrix.
The
Index
M?
is m, right? Index is m. So for example, the only way to check nilpotent is keep multiplying a with itself and seeing when it
Check.
comes 0, right?
Mm.
A square into a, whether it is 0 or not. You're just checking that it is 0 or not, right?
Mm.
So the least number that comes is going to be nilpotent, right? Now there is something called a fifth special type is unitary matrix. Again, this is just a name. Unitary matrix is such a matrix which A into, one second, somebody is at the door. A into A transpose conjugate. Wait, A into A transpose.
Is 0.
A into A transpose is 0. Huh? You have seen this before?
No, I've never seen it in my life.
A into A transpose is equal to I is our orthogonal, no? What is the
We never
difference?
studied any unitary matrix.
Unitary matrices come in quantum mechanics, so I think I don't know why he has mentioned it here, but this is transpose conjugate. This is a unitary matrix. But conjugate means the numbers have to be taken conjugates of those complex numbers.
Oh, okay.
So if you have a elements of the matrix to be complex numbers, then
Take the
take the
this conjugate.
conjugates and then take the transpose, right?
Okay. First the transpose. Wait,
That doesn't make a difference.
Okay.
Okay, so okay, Hermitian and all, I don't think you need to do, no? So I and all will not be necessary, right?
No.
So far, have there been any matrices questions where there's imaginary numbers inside?
No. But they do give it like just to calculate the determinant, not in the
Okay.
question.
So there are some other matrices that we could look at. These are basically unitary matrix, Hermitian matrices, and skew Hermitian. This though comes in quantum mechanics mostly. It doesn't come in maths. It'll come in the quantum physics portions. So right now we'll skip this. I think I don't think this is super important. Okay. Yeah, right now we'll not do it. So mostly the properties are done. Okay, a few more properties are left. So for example, let's do if A is skew symmetric, as well as symmetric, then A is what? Then A is a 0 matrix.
Yeah.
Right?
Yeah.
This is an obvious thing. Then if A is orthogonal, then det of A is plus minus 1.
Yeah.
Right? Because A into A transpose is equal to I. So det of it becomes det of A whole square is equal to I.
Yeah.
Is equal to 1, no?
Yeah.
So then a square matrix is said to be symmetric if A transpose is A, that we already know, all of that we know. Mean diagonal elements of a skew symmetric matrix are 0, whatever. Why is he repeating the same things every time? We have already done all this, right?
Yeah.
Okay. Okay. Then I think theory is over for this portion. So what is left now in this chapter is basically just the Cayley-Hamilton theorem and system of equations, the rules, right? The rules for finding the
number of
Cramer's rule
solutions.
and number of solutions and all of that. So
Yeah.
one class on that we will do. So the topics left are Cayley-Hamilton and system of equation final look, which will be the determinant method and also the matrix method. There are two methods available.
Yeah.
So you can do it with both methods. Mostly this method will be easier.
Yeah.
Determinant method. We have already sort of seen this. So that will be the last class for matrices, the theory part. After that, there are questions and all. Syllabus is over technically. Like by Monday's class, we will be done. Okay. So then let's think about it. You also think about what is the order in which we'll do a revision. So for example, revision of maths, right? If you want to think about it, what are the most difficult chapters for you? Tell me.
For maths,
What is the most problematic stuff?
I think integration.
Integration is the most difficult, huh?
I think so. I don't really find anything that I don't know. Maybe I haven't done enough to find, or I've not done enough hard questions.
This year you have seen whatever topics and last year's topics. What is problematic integration? Okay, just tell me whichever feels like hard.
Last year, what all was there? Means I have to remember. What are the chapters? No, algebra was fine. Maybe
integration, PNC.
Yeah, PNC. Complex numbers. I think.
Complex numbers,
That's,
PNC, integration, trigonometry.
No, trigonometry was fine.
Properties of triangles.
No.
That was not
Easy.
fine.
It's easy.
Oh, great. Okay. On this year, probability is hard.
Oh yeah, hell yeah.
Oh yeah. Very hard. Huh?
Very hard.
Then this year's stuff, matrices determinants is not hard, no?
No, that's not hard.
Okay. And this year's stuff, calculus, what else? Calculus, any
Calculus
chapters?
is easy only.
Integration. Differential equations? You've not yet done it yet, so you feel it is easy, but it's not. Okay.
Say so.
Okay, so this is like a rough plan. Like we'll focus on this and this and this in the beginning, and we'll come to the others also. What I want to do it, the way I want to do it is through test papers. So I am finding my set of papers that we'll be using. So hopefully that should be enough. And next few months will be just problems and all. Make sure that your revision you are doing, okay? Do your revision now.
I started it.
Do your revision. Think of it as a whole syllabus revision now you're doing, so that more or less you are ready for 11th plus 12th. I don't know what will happen next year. Maybe JEE main syllabus will be reduced and all, but advanced should not change. So for you, JEE mains might be a slightly different syllabus. Board syllabus has definitely been reduced a little. So
will it be there like some full proper, like 2 exams will be there of mains, like normal how it is?
Mains will be same only, no? If
like
they are
they
going
won't
to
shift and all.
No, they are already conducting it in September at such a risk. Then by January it will be lower. No? So It will happen. It will just be a slightly reduced syllabus because the NCRT has said that they have reduced some portions. No.
Yeah, but they still have to teach it. They just won't ask the question in the exam.
Yeah, then NCRT will not ask questions in CBSE exams. Then obviously JEE means I don't know. Maybe they will also not ask, but we cannot guarantee that. Yeah. What will be for sure is that JEE Advanced will be unaffected. That will be the same as it is. So you anyway have to prepare what you're doing. You have to prepare to that level.
Yeah.
So yeah. So Monday's class will be the last class for this. I will try to finish those two topics in Monday's class. I will do the whatever properties and all that. I'll do an extra class for Sparsh sometime to finish it. But yeah, that's it. So let's meet on Monday then. Physics also tells Shatiki that I will talk to him also that we have to finish the syllabus. He knows, but around August 20th it should be the rough deadline. 20th or 25th maybe end of the month. You have to finish the physics syllabus. So
We have only like wave optics and
wave optics, he has one more class, I think, right?
we're gonna start ray optics. We finished with wave optics.
Oh,
Sir
you're
said
going to
he
start.
messaged saying we'll start ray optics.
Okay, so ray optics you have to do,
And then those atomic sections. I don't know.
and then modern physics, some chapters are there. Modern physics is the de Broglie principle, dual nature, atomic
Yeah.
structure, nuclear physics. Basically, dual nature of matter, atomic structure, and nuclear physics. But these are all easy stuff because chemistry you've already seen this. So this should not take a lot of time. Mostly the focus will be on, so physics also when we start revision, mostly focus will be first on mechanics and electromagnetism.
Yes, please.
Mechanics, electromagnetism will be first, and then waves plus thermodynamics. Thermodynamics plus ray optics and wave optics is not something that we will stress about because anyway it's a horrible chapter. So ray optics and wave optics is, I mean, I can also not guarantee, so chill about it. What we can guarantee is this should be fully solved. Like this is, I mean, the theory itself is annoying, so it's just formulas and all, and if you know how to apply them, that's it. If the question is an easy formula application, you can do it, but if they are slightly advanced type things, then most of the times you don't know why a particular formula is there. Like the derivation uses many assumptions. So we will try to improve this, but not at the cost of these. This is the major thing that will give you your rank plus modern physics. So these are the portions that we'll try to focus. This is enough to get you a good rank. So you have to make it really strong. Okay, that is the plan. August end or September physics revision will start. And we'll start maths revision in August only. Okay, I'll see you on Monday then.
Yeah.
Okay, bye.
Bye.